Hello, I'm Mr. Troha. We're going to be doing some notes on the outer solar system as well as comets. So the outer solar system contains a lot of trans-Newtonian objects, or TNOs. These are any objects that are outside the range of Neptune, further beyond Neptune as far as their orbits. And there's really three subcategories. There's the Kuiper Belt, there's a scattered disk, and the Oort cloud. And most of the objects out there are just icy, frozen things frozen with gases and whatnot, some rock in there. So the Kuiper Belt, here you can see in a picture where we have Saturn, Jupiter, Uranus, Neptune, and these are all objects that are past or beyond Neptune. So these are 30 to 50 astronomical units away from the sun. They're all considered Kuiper Belt objects, or they're often abbreviated KBO. And even though they were thought to be there, it was not really fully discovered until 1987, which it seemed like a long time to you, but not as long to me. There are many Kuiper Belt objects, and most of them are resonant with Neptune's orbit, which means that it falls along the orbit of the KBOs fall in a ratio to Neptune's orbit. So the scattered disk is just beyond the Kuiper Belt. You can see here 30 astronomical units is about where Neptune is. Moving to the Kuiper Belt are these blue objects in the 30 to 50 range, and then the scattered disk is beyond that. Okay, so these objects are not locked in any particular resonant orbit like the KBOs are. It's believed that comets are coming from this area, and even though there's discussion about it, it really is a pretty recently adopted idea to call this a scattered disk out here. There are definitely some large objects out in that area. So the Oort cloud extends well beyond. It is the outer reaches of our solar system. And so these can have objects as many as 50,000 astronomical units. We were just talking about things in the 50 to 70 range, 50,000 astronomical units. So unlike the Kuiper Belt, which is pretty flat in structure, and kind of think about it as like an asteroid belt but farther away. That's kind of flat. The Oort cloud is a sphere around the entire solar system. And the thoughts are that many of these objects were in the solar system, but then as we passed nearby other stars, the gravity pulled them out into the further reaches. So here's an image. So up here at the top, we have the solar system. We have the Kuiper Belt. Pluto is considered as a Kuiper Belt object. And that whole area falls into this little bitty blue spot here in the center of the Oort cloud. So another scale version in the upper left, we have out to Jupiter. If we look at the upper right, Jupiter is that orange one, and now we're seeing Neptune, so all of our planets as well as the Kuiper Belt here. Sedna is considered out in the scattered disk area. So now we have zoomed out even farther. Here is that Sedna, the rest of our inner solar system, and here would be the Oort cloud. So it's just giving you some to scale situation there. So let's talk for a second about comets. Comets are pretty cool. They're generally just a ball of icy rock most of the time until they start getting closer to the sun. And when they get close to the sun, they start to develop these interesting tails on them, and they're visually pretty exciting to see. So there's a few main things about a comet, our main areas. We have the nucleus, that's the ball of ice and rock in the center there. The coma is kind of like it's a little region of gas around it. And then we have these tails, the ion tail, the hydrogen envelope, and the dust tail. So we'll go into those a little more specifics here. So as I said, we have the nucleus, so it's 1 to 100 kilometers apart. We have the coma, which can be as much as 100,000 kilometers in diameter. And then we have these different tails, the dust tail, the ion tail, can be as much as 500 million kilometers long. That would be like as long as Jupiter. And these tails change their length as they get close to the sun. The tails get longer. And then we have the hydrogen envelope also. So let's talk about the nucleus. It's kind of that heart of the comet. When it's not getting close to the sun, it's just orbiting out in the Kuiper belt or in the scattered disk, and eventually coming towards the sun where we get those tails. So it's mostly dust, ice, not only water, but other ices like methane gas or ammonia. And it can be not very reflective either. It's very difficult to actually see the nucleus in the comet there. The coma is an area of atmosphere almost around it. Because the comet's so small, it doesn't have a very strong gravitational force. So anything that gets evaporated off of the comet, the ice, as the ice evaporates or the dust comes off, it stays in this little atmosphere here. So these vaporized materials from the nucleus. So moving on. So let's talk about the different tails here. The tails get longer as it gets closer to the sun. And interestingly, they're always directed away from the sun. It's kind of an interesting image to see here. The ion tail, they're gases from the comet, but they are ionized, meaning they have an electric charge. So the magnetic field from the sun and from the solar wind actually is what's pushing them away all the time. So that was represented by this blue tail here. It's always directly away from the sun. There's no curve to it. The dust cloud has solar photons strike the material from the coma here. So the actual solar photons, that's the sunlight itself, they're removing some of these tiny, tiny dust particles. And the dust cloud then is this yellow. It actually has a little bit of a curve due to the motion of the comet as it moves around. But because the sun is the thing that's pushing it away, the sunlight is always also pointed away from the sun. So let's look at the another picture of this. Here we have a comet coming in. Notice that we have the ion tail always directed away, and where the dust tail ends up having this curve to it here. Here is Halley's Comet, a very famous comet. So this is as it gets close to the sun. We have the longer tails here. As it gets farther away, those tails decrease. Comets do not follow the orbits of the planets. Notice that the orbits of the planets are these nice, slightly elliptical areas here. These green, we have Halley's Comet that comes in about every 76 years. You'll get an opportunity to see that in your life. And then we have this Hyakutake comet here. It's every 17,000 years. That passed by, so we won't get to see that one again anytime soon. Interesting about comets, comets did crash into the Earth. A lot of these major impacts in early Earth were comets, and they brought water, they brought different organic molecules, that methane we were talking about, which are the precursors of life. So it's potential that those may have brought those things that originally or that ultimately formed amino acids and were able to form life. There was an interesting mission, Deep Impact, that ended up crashing into one of the comets. So they sent it out so they would orbit with the comet and then recorded its impact. So here's one image of it, and here's the visual of it sliding or flying in and crashing into the comet. A couple of interesting comets. The Hyakutake, like I said, that's 17,000 years. That's a very long period comet. The Hale-Bopp was one that came through, and this was in the 70s, I think. That was another very long orbited period, and interesting history with that one. Those are a couple that you might want to do your brochures on. Well, thank you very much. I hope you have a great week. We'll be moving on to talk about more outer solar system things in the next video.